In about 10 minutes, I'll give you a quick tour to my online poster. My name is Joshua, a PhD researcher at the University of Cambridge applying AI and Earth observation data to understand the spatiotemporal changes in regional disaster risk. With me, Ford and Renan from EMI in the Philippines, Robert from Moody's RMS, Christian from German Aerospace Center, and Emily from Cambridge, we present a data-driven probabilistic approach to regional dynamics of building exposure and physical vulnerability towards global disaster risk quantification audit. 2 years ago, when we reached the midterm period of Sendai Framework, an international promise to reduce disaster risk globally, the world has seen inadequate progress because of the lack of data, which puts to question the reliability of regional risk studies. From 2 years to 2 weeks ago, the UNDRR published their strategic framework for 2026 to 2030 and recognized the need for disaggregated data on exposure and vulnerability, where it is important to know the future patterns and projection to enable prospective and probabilistic risk knowledge, and while also underscoring the benefits of using AI. However, in the past years, we have seen an imbalance of efforts among the dimension of risk, where there is still a significant data gap in the aspect of physical vulnerability across space and time. The picture you see is our current state of practice method, facilitated by the Global Earthquake Model or GEM Foundation, which is still low resolution and has to be calibrated and verified for finer-grained applications. Therefore, we center our efforts towards developing a solution, a data-driven probabilistic approach, enabling deep learning, interpretability, and explainability. We present Graph VSSM, a framework that leverages how unstructured is the built environment data through the use of graphical representation, while learning the probabilistic dynamic parameters of exposure E and vulnerability V that comprise our state space model. Why probabilistic? The advantage of such approach is that it allows us to specify some prior expert belief system. And we know that in the field of regional characterization, some methods can be uncertain, some methods can be limited, but still useful. And these methods can serve as our prior. And with that probabilistic assumption, we provide a sense of interpretability and explainability on the dynamic behavior of our exposure and vulnerability patterns. Here, we set the patterns of building height to follow log normality, building presence as Bernoulli, and vulnerability as multinomial or categorical distribution. Given these assumptions we set, let's talk about the picture or the structure of our state space model, consisting of 4 key modules. Module OE relates covariates with exposure patterns. Module TE describes the dynamics and exposure. Module OV relates covariates and exposure patterns with vulnerability categories. And Module TV describes the dynamics in vulnerability categories. These modules connects our variables X, E, and V. Now, time for results. We have 2 kinds of temporal results. One that shows slow urban development in Quezon City, Philippines, and another one that shows fast, rapid changes due to a disaster in Bangladesh and Sierra Leone. Now, let's dive in. We begin with what we have. This is Google Open Buildings 2.5D temporal, a high-resolution data at half a meter resolution and available yearly from 2016 to 2023, and was just released late 2024. That was just last year. Here, we consider 2016 to 2021 temporal periods and then learn the patterns from it to project what could be the future like in 2022 to 2030. After training our model, we are able to express building presence as a dynamic parameter to Bernoulli distribution, or P theta, and their corresponding relaxed samples. Same goes for building height. We extract a dynamic mean and standard deviation for every pixel and produce probabilistic samples of building height. Also, For our vulnerability, we had area-based approach as a way to characterize the regional distribution of categories, and we produced and mapped dynamic parameters of each category using the categorical multinomial distribution. And with that, following the risk equation, we can compute for some risk metrics like expected injuries or expected fatalities for an attempt to plot and understand the trends of a dynamic regional earthquake risk perspective, as well as with the corresponding map in the entire Quezon City in the Philippines to locate concerning areas. Next up is the story of disaster aftermath. We also apply the same approach, and we essentially update a prior information to come up with a posterior distribution of vulnerability labels across space and across time, also following categorical multinomial distribution. We extended the analysis by showing here a graphical illustration of the expected transition between vulnerability classes and first-order transition matrix that are both useful as a regional summary of dynamic vulnerability characterization and dynamic risk assessment. Another part of our results is the application to larger continental dataset like Meteor data. Meteor data is an effort back in 2017 where several agencies and organizations, with the funding from UK AID and Space Agency, they mapped the regional spatial distribution of physical vulnerability in least developed countries. Because we have new temporal exposure dataset, we wonder why not try integrating them and come up with a temporally defined dataset, producing Meteor 2.5D, which is 5 times finer or higher resolution with 11 temporal periods from 1975 to 2030. Now let's dive in. So what's Meteor 2.5D? It's an open geospatial dataset that spatiotemporally enhances the Meteor dataset back in 2017. It refines and corrects. It downscales across space and time. And it advances and explores the possibility of emerging AI learning techniques. As we do not have the luxury of time, we'll showcase one country, Guinea. To present this nicely, we have 4 columns. First column is our prior data, vulnerability class proportion from Meteor at 450 meter resolution and non-temporal. Second column is the building height data from World Settlement Footprint WSF3D dataset by German Aerospace Center. It's an input at 90 meter resolution, also non-temporal. And after training our model, we come up with the inferred vulnerability classes. Third column is the net building height data from the Global Human Settlement Layer products. It's an input at 90 meter resolution, also non-temporal. And after training our model, we come up with the inferred vulnerability classes. And the fourth column is the built-up volume from Global Human Settlement Layer as well. It's an input at 90 meter resolution, but this time, temporal. And after training our model, we come up with the inferred vulnerability classes. Here, as an example, we have the spatial map of informal construction type with the WSF3D building height. We have a posterior map of informal construction type. Same goes for GHS net building height. We have another version of posterior map of informal construction type. And for the temporal built-up volume, we also follow the same approach, but this time offering us temporal maps as well from 1975 to 2030. And with that, we hope to continue the efforts of risk auditing as we reach 2030 and beyond. We have seen in the past more efforts towards dynamic exposure and dynamic hazard modeling, but this time we talk another equally important and uniquely challenging aspect of the spatio-temporal distribution of physical vulnerability characteristics. We also realize that the work we're doing has contribution to broader urban studies, where information is always expressed at a larger scale. Due to the difficulty in manually surveying the building one by one, we hope our framework advances some of these questions we have in this space. And as we're excited for the future and the development of this work, we really think, what if we incorporate building level information like retrofit, demolition, or damage, even sparse or incomplete, to the learning optimization of our deep neural networks. These flexibility, and an exciting kind of calibration would offer us improvement in overall performance and would most reflect the reality on the ground. Until then, this poster is just a starting point for more future developments in using AI and EO for building exposure and physical vulnerability modeling at large spatiotemporal scales, all towards global disaster risk quantification audit. Thank you everyone for visiting. Let me quickly acknowledge our funding, the UKRI, APSRC, and some resources you can check for more information, like the survey where you can add your feedback or any follow-ups. And the full paper will be presenting in AAAI Conference on AI in January 2026 in Singapore. That's all for it for now. Bye.